Almost there. We've got about 10 more seconds. I think it's official. Welcome back, everyone. Any questions before we get started with week 2? Maybe we can drop that down if you like. Did you have one for the class, maybe?
Yeah.
Or I could answer your question after class too, really kind of what works best. Okay, awesome. And if you folks did have questions, maybe for the whole class, I'm not opposed to spending some of the initial class time going over maybe a nasty thing on the homework or a weird point or maybe a mistake I made on the lecture prior. Always happy to revisit. Well, other questions or comments then before we begin? Okay, well, let's go off then to our current, well, let me pause right here. Just a reminder, assignment 1 is posted to the Moodle website. And because it's only week 2 and we said a lot of stuff, don't forget if you click right here, it'll take you to the exercises from the most recent edition of the textbook, as well as the solutions on a section by section basis. Also, if you want your files in WordNote, these are blank in Word document. You can always find them there, as well as the recorded lectures. And last reminder, every time you finish this section, you can always click on these again on the body of the Moodle website. And these will be the PDFs of our lecture notes and the solutions posted as well. So the other reminder was, of course, assignment 1 is out. They're considered officially assigned on Thursday, once we get the last section in, and it will be due on Thursday of this week. If you want to turn it in early, I'm not opposed to that. You can turn it in at any time. Just say, drop it right here, and I just grab everything before I go. You can also email them, and that's going to be perfectly fine as well. Another point of interest about this is I had a lot of feedback from folks saying they really appreciate like the Moodle's official due date right here because it puts something in your calculator, really helpful for organization. But it means I also have to put in a time, and I just put when class started. You can turn in your assignment after class, that's just fine. If you forgot to bring it to class and you emailed it at say 9 o'clock, that's okay as well. Maybe you had a question about a problem right after class and you needed to change it. It's okay to make those changes and turn it in at any time. As long as it's turned in on August 31, it's considered on time. Does that make sense to folks? Awesome. And that's essentially how all the assignments are going to work. Assignment 2 is now being built right here. You click on it. Okay, I got the stuff in here for section 2.5. If there's anything missing, it just doesn't look right, just send me an email. I'll go into there and fix it as soon as possible. Oh, that's too far. There we go. So I only have the first portion of assignment 2. And again, I don't put all the problems I want down only because of pacing issues. If for some reason we just spent, say, a lot of extra time in 2.6, and I couldn't get to a problem in 2.7 for the homework that I want to show, I might unassign that problem just so the class kind of doesn't always get bogged down on old stuff. Well, I guess that's about where we're at before we get started. Any questions, folks, before we jump to 2.5? Okay, we mentioned a lot in the last sections that continuity, when you can make it work, is one of the bigger tricks on taking limits. And when we were in section 2.3, looking through the limit laws, really the direct substitution property right down here, this is what continuity looks like. Continuity is saying that you took a limit as the variable got closer and closer to a of f of x, and your output is f of a. In other words, we just substitute a right inside there, and continuity gives us the ability to do that exactly. In the notes, though, sure, the formulas look about the same, but it does get a little bit tricky. It says here, a function f is continuous at a number a if this limit down below exists. So it's not any does not exist at all. You have to get a number out. And even more so, it's not an arbitrary number. That number has to be exactly f of a. So again, that's the idea of direct substitution. Let me blow this up for just a bit. Where we took this value, the a, essentially plugged right inside there, giving us the f of a altogether. So this whole formula could be paraphrased by saying, direct substitution. And in other words, direct substitution only works if you know your function is continuous, where that value is heading towards in the limit, that a value right there. So knowledge about continuity means you really don't have to do any fancy tricks or backflips on the limits. You just plug in the number directly into the function. Any questions at all, folks, about the definition here? Okay, let me say if it's not continuous at the number a, then it's discontinuous at a. Kind of makes sense. It's just a rearrangement of the words there. So let's do a couple fast graphs just to get a feel for what this looks like. So here's my a value. I want this one to be for continuity. And here's a second graph. I'm going to try to draw them sort of similar, but the difference is right here, we're going for a discontinuity. I'll do the graph in blue. Let me do a circle that goes like this, but solid at a. And the curve just comes on through like that. There's really nothing special about that solid dot. I'm just emphasizing a point on the graph if I do it in this kind of way. And right here is the height f of a. Now let's do this graph one more time. This is going to be the one where I'm going to draw a discontinuity at a. I'm going to put in an open circle this time. I'm attempting to draw the same blue graphs, but it will only be so similar. Comes up, goes in, and then shoots out like before. So two very similar looking graphs. As it stands, the function is not even defined at a, how I plotted it. That alone is enough to break continuity right in this picture. But it gets even worse because you can define the function if you wanted to. I'm going to put a solid dot. And on this graph, here's where f of a would go. It's not at this height like it was on the left graph, because the solid dot says that's where the function value actually occurs, at that height instead. Any questions at the moment? Okay, so in deciding if a limit exists on these graphs and using the definition, these are the major things we're looking at right here. As we get closer and closer to a, is the height of the graph of y equals f of x equal to f of a? If you can say yes there, then it's continuous. So let's do two limits at once. On this one, limit as x tends towards a of f of x equals, and now as we follow this, we have to get close and close to a, but the outputs themselves are all very, very close to f of a. Does that make sense to folks looking at it visually? Awesome. So we get to say here that this is equal to f of a. And so our conclusion is f is continuous at a. Let me say x equals a, just to be specific. So that's what continuity looks like. And sometimes people phrase it in this way. The graph of a function is continuous if, when you go to graph it, you never lift up your pen from the paper. It's just one continuous and unbroken curve. On this one, you absolutely would have to lift up your pen to make the open circle and the solid up above. So you can't draw this with one clean pen stroke. That's a discontinuous curve. But also, it's because of what goes wrong in this limit right here as well. So let's analyze the second graph limit. We're once again taking the limit as x goes to a. On the graph of the function, f of x. And I didn't put a value here. Let's put just a really fast value. Let's call this maybe 2. So when we get closer and closer to a on this graph, if I place that right, one more try, what happens is the height of the curve is getting closer and closer to 2. It is not approaching f of a this time. This is the case where we have discontinuity because the equality right here is essentially broken. It's not equal to f of a, or let me write it slightly better. It's equal to 2, but then it's not equal to f of a. F of a is just slightly higher. So in this picture, we would say f is discontinuous at x equals a. This is just one kind of discontinuity. There's going to be a couple more that we'll take a look at as we go further and further in these notes. First, any comments at the moment? Okay, well, these two examples are done for definition 1, but what the heck, let's add just one really fast comment. This kind of discontinuity is called removable. So let me put here just a quick note. Remove a bowl discontinuity. What makes it removable is you can fix this by simply taking this dot right here, remove it, and fill in this dot. Now you have continuity. If moving just one point can make the whole thing continuous, we call that a removable discontinuity. Well, other questions at all, folks, with continuity? Yeah.
So, if the limit approaches infinity, and that's like, I know it's not possible to write it as, limit is approaches infinity, is that continuous with this all the
Gotcha. So you're saying infinity is right here by the x,
No,
or you meaning
so
on the
X-
output?
Yeah.
Oh, gotcha. So I see what you're saying. So if we say limit as x approaches a of f of x equals infinity, then this wouldn't be continuity. I think you said it's because when you get that infinity, that's a way it did not exist. And that's the problem right here. When we said continuity here, the number f of a exists as a real number. So this limit itself exists. We put in a real number there. And that's a good point to raise already. If this one's a removable discontinuity, anytime you get an infinity like right there, that would be called an infinite discontinuity. And there's still another kind, the jump discontinuity. But does that answer your question there? Awesome. Other questions at the moment? Okay, so continuity at the moment, just visualize these kinds of graphs. Here's where it gets a little bit hairy, unfortunately. We have the idea of a left side limit and an idea of a right side limit, whether you put a plus or a minus above that a. And that means we also have an idea of left-hand continuity and right-hand continuity. So this one's continuous on both sides. This one's discontinuous at both sides. So let's do some pictures where it's only continuous from the right or it's only continuous from the left. So two more limits, and then we're done with definitions of continuity, except for this one here, just a small add-on. Any questions first before we consider these? Okay, looking at the structure here, notice they both have this feature. Limit as x approaches a, limit as x approaches a. Now the difference is that plus right here and that minus right there. We're approaching from a specific direction this time. And if the output is just f of a on both of those, then we'd still have continuity, but from one side or the other. So let's do one graph that shows both of these issues at once. So down below here, I'll have a value A where something interesting happens. I'll call this a value B where something else happens. And the curve will be in blue. So I'm going to start by going, say, about like this, about like this. So two open circles. Let the curve start by going in, say, that way. Let's fill this in solid. And we can let the curve just start right there. So it's filled in solid in that location. And coming up over here, we'll throw a small dot down below. Let's fill in this solid dot below solid. And the curve can just continue off indefinitely in that direction. So that's the entire curve so far. I'm sensing I would want more space, so let's just move that over. And this graph has some weird issues. So as we look at this, something's happening around A, something's happening around B. There's continuity there, but only from one single side. Let's maybe start on this one. If you were to take a limit here, here's how you'd have to write it. Lim as x approaches A, I have to approach from a specific direction, meaning I have to put a specific symbol up here, either a plus or a minus. Anyone see which one it must be? Sorry, say again. Turns out it's not minus on this one, but it's only because when you're right at A, you're only going to be on the right-hand side or A exactly. So if you can only be on the right-hand side, that means we have to put a plus there. It's only because there's no values to the left at all that we have to do that whole thing. We need to take f of x here in the limit and see what it comes out as. Well, right here, that's where f of a would be. And as you get closer and closer to a coming in from the left, this curve gets closer and closer to the height of f of a. The solid dot turns out to be irrelevant on this. Well, hang on, no, it turns out to be highly relevant. Let me put a quick note there. The solid dot is required. Now, why is that? If we didn't have the solid dot, we wouldn't be able to put this in. F of a itself. So as we got closer and closer to a from the right, the height got closer and closer to f of a. If you take away that solid dot, it would have looked like this instead. Oh, not like that. These things are hard to delete sometimes. They look like this. We've broken that. You can't plug a in anywhere at all because it's undefined. If I put my solid dot down here, I've still broken continuity because it's not f of a. F of a is way above. So this solid dot had to be specifically right here to make this work out. So now we're back to this definition by the red dot. The limit as x approached a from the right with that plus sign does in fact equal f of a. And that means we get to say below right here, this one is continuous from the right. And the plus symbol there is a bit of a reminder that that's the direction of continuity as well. Thank goodness those kind of go together, else that'd be very tricky, I'd say. Does it make sense to focus on that first limit right here? Okay, now when we look at this one, let's see what should happen here. Oh dear. I don't quite like where my solid dots went. Sorry to everyone working in pen. Let me rearrange my solid dots. I want to open here, going down. I should have had this one solid. Again, sorry if you're working in pen today. I'll try to not make those mistakes too often. The reason I needed this one solid is I'm trying to show continuity from the left this time. And the placement of that solid dot is absolutely critical. So let's do this limit one more time. This time I'm worried about being near the value b this time. So it's going to be the limit as x approaches b. And I want to approach it from a specific direction. You can approach from the left, you can approach from the right. Let's do it from the left this time. So I'll put the little negative sign there to say we're only on this end of the curve as we go through the limit. So this will be for the function f of x. Let me add one last point on the graph. Where that blue line is, that blue dot rather, that'll be the height f of b. And would you all agree that if we took this limit as x approaches b from the left, the height is getting closer and closer to f right at b? Also looks like we're in agreement. So that means we can put f of b right here and now say this is continuous from the left. Only because of that solid dot right here is what made that happen. Does that make sense to folks so far? Okay. Well, that's continuity from the left, continuity from the right. And let me just add here, just to finish this off, add x equals b for this one, and add x equals a for this one. Let me underline it. I forgot to say what value we were talking about, so just a little bit more description there and there. Now, if we want to talk about the range over which we're continuous, that's what this last definition here is talking about. Sometimes we're not talking about a specific number like a, we want to say it's continuous all the way from A to B in this way. Or we might say from B going up to infinity on the second part. So we sometimes mention having continuity on an interval. I would say the definitions 2 and 1 are much more important. This is more just of a technicality if we're talking about an entire interval itself. So that's what continuity means and what it looks like so far. What we're going to do on these notes is take a look at a couple more graphs. Say this one here. We'll design our own function just to see the whole process going backwards. Then the big theorems come in for continuity, and these are extremely powerful theorems. And particularly theorem number 7 gives you a catalog of functions which are continuous. This is tremendous because this will tell you every function where you can just use direct substitution. None of the trickiness we had to do in just section 2.3. So that'll be the idea of the notes. And then here, we'll just take more and more limits to end the day. Well, any questions at all, folks, with the core definitions before we get started? Okay, let's try this all as a review by considering one more graph. So in example 1, again, this is just one single function that we're trying to look at. It says for part A, state the numbers where the graph is discontinuous. We're just looking for the discontinuities. And we're also going to classify them as we go. So this will be where we define the type of discontinuities we see. So let's begin by saying x equals, that'll be our first location. As you read the graph going left to right, anyone see where the first problem point, the first discontinuity would be? Like a couple people saying 1, do you all agree? Absolutely. Again, you can't draw this curve without lifting up your pencil right here. There's an entire hole in the graph. And so at x equals 1, that's our discontinuity. As far as the type, we mentioned before that this one is considered removable. What makes this discontinuity removable, just as a reminder, is define the function like that, then no problem. You've removed the discontinuity with one change of one single point. Then as we go left to right, here's another problem point right at x equals 2. And this one is also considered to be removable. We're almost getting to the jump. And I see why you might say that. You could jump this point back up to that location to fix the discontinuity, but still confusingly, it's considered removable. Sorry, say again? Which ones? Are you talking about x equals 2? Well, at x equals 2, this one's considered removable because if you redefine right here, you remove the discontinuity like before. That's part B. Oh, gotcha. We'll get there shortly. Let me know if we're going to get about what you're expecting on those. But x equals 2, this one's considered removable. And then there's a comment about jump discontinuities. That one's absolutely coming up. And this is what we mean by an entire jump. If not just one point has, oh, let me fix this right here. If more than one point has an issue, if the whole curve has been brought down by a certain distance, disconnecting it, that's what we mean by an entire jump discontinuity. Does that make sense to folks at the moment? Awesome. When we have jump discontinuities, yeah, that's when where continuity could exist from the left or from the right. And like we were saying earlier, the first two have neither. But let's go to this one. Notice there's something weird happening here, but you can draw that without lifting up your pencil. So it's absolutely continuous, even though it got very sharp at that location. But x equals 4 is the next discontinuity, and this one is a jump. Does that make sense to folks on classifying this one here? Awesome. Finally, anyone see where the last discontinuity would be? At 5, everyone agree? Awesome. And this goes back to an earlier comment. If we took the limit as x goes to 5 of the function f of x, that limit would come out as infinity. It does not exist, and that's a particular way it doesn't exist. It's going up on either end of that vertical asymptote. But if you output infinity, that means you have then infinite discontinuity. So we'll say right here, x equals 5. If it's going, say this way, you're saying? Oh, I gotcha. So if it was, you said right side did exist, it would still be an infinite, yeah. Absolutely. Oh, I need to scribble out more. There we go. So we'll say x equals 5, infinite. Discontinuity. So those are the only three we're going to discuss in class. Sorry, go ahead. Oh, gotcha. So you're saying, that's what I was thinking the earlier comment was. So what if it looks, say, like this instead, and that curve was gone? We would still have the same result, but we would have to modify by saying, this one heading towards 5 from the left goes to infinity. The limit has got 5, x goes to 5 from the right goes to infinity. Essentially, as long as you can put one of these there with either a plus or a minus, if the arrows go different ways, you still have an infinite discontinuity. Or maybe a cleaner way to say it, if there is a vertical asymptote, you have found an infinite discontinuity. Weird things can happen around it, but as long as there exists, you have one. In fact, let's put that on the notes. Let's say right here, if there is any vertical asymptote, there will be an infinite discontinuity. Does that make sense, folks, seeing it that way there? Awesome. Lots of ways to see it. Essentially, if you have infinity as an output to a limit, any limit, you'll have a vertical asymptote. And that's what's enough to give the infinite discontinuity right here. So part A is kind of nice. It's definitely had new stuff. We're saying what kinds of discontinuities we have. There's other kinds as well, but these are the main ones we're going to focus on this class: removable, jump, and infinite. Well, part B is a little bit tricky. For each one, we have to discuss the type of continuity. And there's some hints on that already. For 1 and 2, there is no continuity, neither from the left nor from the right. And that's really kind of surprising. But the reason for what's going wrong at 1, if there was continuity, you would have been able to say limit as x tends towards 1 of f of x. We can do that limit. It works. And in fact, the limit comes out as 1 as well, right? But this is what's going wrong. The reason the limit does not exist at all is continuity is saying something much, much more strong than that at all. What continuity is saying is you put the function at 1 inside, not 1 itself. So coming back down here, if I try to say f at 1, well, now we have a major problem, right? F at 1 is undefined. So the major definition for continuity must have something right there, but there's no meaning. That didn't exist at all. So that means there is no continuity right here. It's neither, like was mentioned earlier. Does that make sense to folks at the moment? Okay, so let me put here, it didn't ask for an explanation, but let's put in our explanations because it's tricky enough. It'll help with the notes, I think. So we'll say here, x equals 1, neither. And the explanation I'll put in parentheses. For this one, the problem is f at 1 is undefined. And that's a required portion to get some kind of continuity out of this. Now, in this next one, f of 2 is defined, so that's nice. f of 2 equals 1. But there's a second problem here. Let's work through it and see what happens. X equals 2. Well, like was mentioned earlier, this one is also neither. And the problem here is, let's take a limit. Take the limit as x tends towards 2 of f of x. It does exist. We go up here, we get closer and closer to the height of 2 on the left. On the right, we're also getting closer and closer to a height of 2. But again, we're in a big trouble because it's not 2 that goes there. It's not equal to f at 2, which is 1. We need to put f of 2 there, not 2 itself. F of 2 came out as a height 1, and there's no fixing that. That point is going to stay right exactly where it is. We're not going to change the graph. And so that's what goes wrong on that second one. Any questions so far, folks? Okay. Now it says for part B, for each discontinuity, determining if we're continuous from the left, right, or neither. We had 2 neithers. But what about at 4? There is continuity from one side, but not the other. You want to see which side? Yeah, go ahead. It's definitely kind of tricky, right? From the left, absolutely. Good call, folks. This one's continuous from the left. It's all about those solid dots. I struggled on those with my first graph I wrote. I thought, oh, that solid dot has to be somewhere else. If we go back to that graph just for a moment, here's the trick visually. You're coming in and you land on a solid dot that's continuous from the left as you go left. You're coming into the right and land on a solid dot. That's continuity from the right. Let me read this again. No, I think I got that backwards. Let me try one more time. We're coming in from the right. We're only taking upper values. We have continuity from the right, like on this graph. Definitely a really tricky problem. On this one, continuous from the left meant we were only coming in from the left. I think the better thing to take a look at on both of these is definitely going to be the directionality right there. If you put in the limit and you put plus, that's continuity from the right. And yes, we're coming in from the right in that kind of way. Too many little labels and directions. Does that make sense to folks so far? Okay, then coming down on this one, we come in and we're coming into a board from the left and we land on a dot. Like you all said, that is continuity from the left. So let's put here, x equals 3. From the left. Now let's check this out. You don't have to write what we're putting in orange. That's the explanation. But if you write this out, it sometimes helps a lot. If we said continuous from the left, we should be able to take the limit as x approaches 3. I put a negative sign there to say it's coming in from the left of f of x. Let's go back up to the graph here. We're coming in from 3, coming in from the left. It lands right at a solid dot, and the height of that solid dot would be right at f of 4. So we could put, oh geez, that should have said 4. Sorry about that, folks. My problem point, if I circle that, I think that'll help me out, was 4 from the left. It equals f of 4, only because of that solid dot. And so that little negative sign that gave us the limit also is what's giving us continuity coming in from the left, all at the same time. Ooh, definitely a tough graph though. Does that make sense so far, folks? Okay, so far, if you have a removable discontinuity, it's going to be neither on those every single time. Oh yeah, go ahead. Oh yeah, I wrote that twice as a mistake. Thanks for spotting that. X equals 4. So we're right at here. So on the removables, they're all neither. But the moment you get to a jump discontinuity, you have a possibility on continuity on one end or the other. But what about this one at infinity? Any volunteers for what that should be? Left, right, or neither? Sorry, did I hear neither? Yeah, absolutely. If you have an infinite discontinuity like this one, the curves going up, or maybe in a different direction or anything like that, this one is neither as well. The only way to have continuity from the left or the right is take away the vertical asymptote and maybe make the graph stop at some height. Now you have some kind of continuity. If it's always moving upwards, it's never settling down at any number. So these limits, they don't exist at all, meaning there's no continuity either. So that was at x equals 5. I will just say neither. So I think probably the big thing to take away from this whole problem is the only one that had a possibility was the one that was a jump discontinuity. So jump discontinuities are the only ones that have possibility from one side or the other.
Only the jump.
Exactly, yes.
How do they?
How would they become neither? If you put, you're saying for a jump discontinuity, if I put an open circle right here, and then a solid dot way up here. So now it doesn't matter if you're coming in from the left, you're not getting close to that point. It's a huge distance upwards. Coming in from the bottom, same kind of issue. Does that make sense with that question there? Gotcha. Well, so far, that's the major things to watch out for on these graphs when you're considering continuity or single-sided continuity. Next thing we're going to do, always a little bit of a challenge, is draw our own graph. So here's the next thing. After that, we're going to take a look at some helpful theorems and we'll crank out some limits using continuity. That's exciting. So very different from section 2.3. First, a little bit of notation. You may have seen this symbol before. It's going to be used a good amount in our book. I'll occasionally use it here or there. But if you ever see that symbol, it's just a way to refer to the set of real numbers. So it's referred to as a chalkboard boldar, the set of all real numbers, and in interval notation, it would look just like that. The only reason it comes into play here is because we're going to sketch a function, and the domain has to be R, all real numbers altogether. So some way, somehow, you have to do a function value for every single real number when you go to sketch this graph. We'll come back to that first condition because it's a tricky one, but we won't worry about it for the moment. Let's first study these things down below, those 4 conditions. So first thing we ought to do is let's just make a really long horizontal axis. So things are kind of spread out. Because it's a sketching example, also keep in mind there's always going to be more than one right answer to this. It just has to hit all these kinds of issues right here. Now, next thing to look, let's see what our horizontal scale is going to be involved at. We have -1, -3, 2, and 5. So an issue right here at -1, then -2. Something happens at -3. Here's 1, 2, 3, 4, 5. So all I'm trying to do right now is not do everything at once, just organizing the axes. For the vertical axis, doesn't look like there's any information, so I don't think we have to worry about any tick marks here. Now let's just go down the line. I'll plot the function in blue, and it first says the function is continuous, only coming in from the left at -1. Now, we have single-sided discontinuity, which means immediately there should be a jump discontinuity. If we're doing a jump discontinuity, put in 2 open dots, and now we just have to make continuity from the left work. I'll make it come in from the left like this, come out like that. My strategy at the moment is I'm only graphing a little bit of the function. I don't want to make it go too wide and then conflict with other conditions. And last thing, I'll leave this up to the class. To make continuity from the left happen, should we fill in the lower dot or the upper dot? Lower? Absolutely. It's going to be the lower for left-handed continuity. So if you come in from the left and hit a solid dot, that's what left-hand continuity looks like visually. Yeah, go ahead. What do you mean 2 continuous on outside?
So basically, you have
Sorry, I couldn't quite follow that. Are you saying like two solid dots like that?
Yeah, but it's in, so that you see, and there's one. Two different-
Let me try to get to that first part. So two dots, say like that. And then what was the other part?
It would be both sides.
Mhm.
Below one would be a distance, and then above that would be another distance.
So something like that. Probably, but one issue is really I'm only trying to do this right here. I'm only trying to cause an issue on -1, not on other parts of the graph. But did you have a question about what would happen here instead?
With
Well, you have continuity from the left at this point, continuity from the right at that point. Does that answer your question about that? Oh, gotcha. If you're coming in from the left and you hit a solid dot, say on this graph so far, that's continuity from the left. If we instead change what was solid, say go like that, that's continuity from the right instead. Does that make sense there? Gotcha. Other questions so far? Okay, let me bring it back to right about there we go. So we forced continuity from the left right at -1. I'll put a little check mark here just to remind myself that condition's done. And now let's go to this one. This one's not asking for specific discontinuity or continuity. It just says do a jump at -3. So really the strategy here is two open circles will absolutely do the job. I'm going to connect this curve all the way over to this one. And I have to be very careful because keep in mind, the vertical line test must pass. So coming out from here, we could just make it go to the left forever in that way. Does that make sense so far? Yeah, go ahead. Oh yeah, absolutely. So where it is above or below the x-axis, really up to you pretty much. Some reason I put it above the x-axis, no apparent reason though. Other questions or comments so far? Okay, so I have a jump discontinuity at -3. It jumped, so we're in good shape there. But I've actually have a problem right here with how the graph looks like right at -3. It's not defined there. We need to fix that. Any suggestions on what to do? Yeah, go ahead. Exactly. And there's no information on single side continuity, so you could do anything, right? Fill in the top dot, fill in the bottom dot, just don't fill in both because then that violates the vertical line test. You can even do something wild and fill it in way down here. -3, it takes off a negative value finally for the first time. So anything like that would fit the bill. I'll try not to do anything too weird since then it looks weird on the notes. I'll just fill in one of these. I think that's the more normal thing to do. So all we're trying to do is force every value on the x-axis to be a domain value. It probably wouldn't be worth a lot if that was an exam question here, maybe like one single point. So I think we're still okay on the first one. Let's go down to condition number 4. It says there's a removable discontinuity at 2. So if there's a removable, all we need to do is poke a hole right there. Now I'm going to continue the graph starting from this right here. Come on out. And now we have a removable discontinuity. Same issue as before, we have to put a solid dot somewhere, but this time you can't put it right here at 2. You've now removed the removable discontinuity. So put a solid dot either above or below and you'll be all set. I'll put mine about below to really make a negative value this time. So you have discontinuity right here, which is removable. And the domain still includes 2 because of that solid dot there. Any questions about that so far? Awesome. Well, we're getting through it. So this one's done. The last thing it asks us to do is make the function be continuous from the right at x = 5. So continuity from the right means we need to put in 2 more open circles. We need to let our curve connect to them. But as I draw this curve in, should it connect to the top or the bottom? Sorry, say again. Exactly, that's kind of weird, right? Let's say here, continuity from the right. Let's maybe make it go in from the right, say like this. I'll make it hit the bottom like that. Now we're kind of forcing an issue, right? At this stage, where should this curve go? To the top open circle or the bottom? I agree. In this case, we don't have any choice any longer. Can make it go to the top like that. Fill in this bottom one. And with that bottom one filled in, this is what's giving us continuity from the right-hand side this time. Does that make sense to folks so far? Yeah, go ahead.
If there wasn't a bonus, it's number that has to have real numbers,
Mhm.
would just continuity have to have both the dots, so then I'm going to be discontinuous on both sides.
So you're saying if we didn't have the restriction on all real numbers, could we do something like, say, that, for example, is what you're asking?
No, I just feel open circles.
Oh, gotcha. So something maybe like that, and just stopping right here.
Yeah.
Yeah, that would work. We would still have to fill in this one here, just to make continuity from the right at x equals 5.
Yeah, like there wasn't.
Oh, gotcha. So if we took out, you're saying this condition right here,
Yeah,
we're not worried about that condition either. We want a removable discontinuity at 2. And yeah, if you just made it look like that, that would have been okay.
but then maybe it's not discontinuity to an open circle.
Your jump discontinuity at, say, 5 right here.
Yeah,
Yeah, you could put in another open circle and make it continue out.
and that works for them.
Yeah, absolutely.
Okay,
Yeah, jump discontinuity doesn't have to have either filled in. It's only going to be if you have continuity from one side or the other that's forcing it.
okay, thank you.
Yep, you bet. So I think we had continuity from the right, so we'll fill that one in. Let the curve just carry on. So it looks like we did all conditions. Any questions about that so far, folks? Okay, well, looking at it one more time, these graphs again are really tricky. I had to revise some notes just above. Let's see if it all works out. So going down the list one more time, the function has to be continuous from the left at -1. That means as we head into -1, it lands into a solid dot before it jumps. So we're good there. Jump discontinuity at -3, that's what we did. We were not worried about single side continuity there, so we just filled in however we wanted. Removable discontinuity at 2, that's what it looks like. That's just a domain condition, so the domain is still all real numbers. F of 2 had to exist. And continuity from the right means, as you come in from the right, it stays solid on that jump discontinuity there. So I think we did it, folks. That's all 5 conditions. Does it look okay to everyone so far? Awesome. Any last questions or comments about it? Okay, well, we're getting to our last couple examples for the day. And the first example of the 2 is not an example that I would actually ask in the homework. It's more of how to tie together this information to just get a feel for what all these new theorems are saying. So it doesn't even say example there, just to help out. It says explain why the function x times the square cosine of the square root of x squared plus 1 is continuous on R. So that sounds like a nasty thing to do, but we can just rationalize our way through it using just ordinary words and the theorems above. So out of all these theorems, again, theorem number 7 is extremely powerful, but we'll show how the rest of them combine. There's lots of different kinds of functions here, so let me organize this way. There's the x function, there's the x squared plus 1 function, and then there's the cosine function. So let's start giving these things names. So let's say u of x equals x will be my first function. Let me skip to the one in blue. I'll call it just v of x equals x squared plus 1. And between those two functions, we can go down to theorem 7, and this part right here says the following types of functions are continuous at every number in their domains. And one of them is polynomials. The good news about polynomials is their domain is all real numbers always. So we can say right here, are continuous by theorem 7 on R. You can plug any real number you like in there whatsoever. So great functions. Any questions about that so far? Okay, well, there's more functions. Another one is, let's go to that trig function, and there's even one more. I'm running out of the ability to highlight. Let's say W of X equals cosine X. What kind of function would you classify this one as in theorem 7? Exactly. Every trigonometric function is continuous on its domain. And it just happens to be sine and cosine has domain all real numbers. So there's never a problem with those functions. So this is continuous. I'll say cont, short for continuity, whenever we're trying to just not write as much. By theorem 7, from this portion right here. And again, let's see, we had the x function, the cosine function, the x squared plus 1 function, and finally the square root function, last one. Let's call it maybe y of x equals square root x. It's a square root function, but we could also call it, let's see here, a root function. That one is continuous on its domain, but it happens to have domain of the non-negative real numbers. So let's say here is continuous on this interval from 0 going off to positive infinity. So there's a lot of functions here. Each one of these individual components that we separated out are continuous functions by theorem 7. But it said explain why f of x, the entire function itself, has to be continuous. Well, we're getting there. Next thing we should think about is the compositions that we're dealing with. First, any questions at the moment, folks? Okay, again, think of what we're doing right here as just a way for us to absorb these theorems before we're about to use them in other problems. Now, when we see cosine of square root of x squared plus 1, that's just one big function composition between 3 different functions. And looking at theorem number 9, it says if you have functions that are continuous, if g is continuous at a and f is continuous at g of a, then the composite function f of g of x, defined in this way, is also continuous. That's what we're dealing with, cosine of square root of x squared plus 1. It's a composition between 3 functions, still continuous through theorem number 9. Let's say right here, the function that goes cosine of the square root of x squared plus 1 is continuous by theorem 9. So another powerful theorem. So all I know for the moment is the right factor, cosine root x squared plus 1 is continuous. X is also continuous. And if we scroll up to the top here, or maybe just copy paste it for a moment, there's other ways to combine functions, say just multiply them together. This one right here is what we're going to look at next to finally give the full explanation. We know that x in green is continuous, the cosine and the composition is also continuous. So the product of them together, that's like taking 2 functions, multiplying f times g, has to also be continuous. So I'll say here, a little triangle just to say, therefore, f of x, which is equal to x multiplying cosine. And to show the composition more cleanly, you could put extra parentheses in if you like. It's cosine of the square root of x squared plus 1 is continuous. So what we did there, think of the x as being the f, and think of the cosine root x squared plus 1 as being the g in that combination there. We try to get that highlighting in. Gee, that's kind of hard. Let me try one more time. And that's the idea of theorem 4. We already knew x was continuous, and we also knew cosine root x squared plus 1 was continuous. You can add them, subtract them, scale or multiply them, multiply or divide with that provision on dividing by 0, and you still have a continuous function. So that's, again, an exercise in going through theorems 4, 7, 8, and 9. We haven't used theorem number 8 just yet, but we will. It's just there because they go together. And it's also how you could just take a look at a function and decide for yourself, if I had to prove it's really continuous, could I do it? The work looks like this. It's weird because it's just a bunch of words, no actual numbers really moving around too often. Well, any questions, folks, before we try out continuity? Okay, as we're about to do this, we're thinking about what functions are continuous. That's what theorems 4, 7, 8, and 9 are giving us. But then, never forget this. The moment you have continuity, evaluating the limit is just that. Best limit ever, you just plug in the number. If you've lost continuity, you might have to do something else. That was what was happening in section 2.3 until we simplified the function, getting a continuous one and directly substituting. So let's try this out finally on example 3. Any questions first, folks, before we give this a try? Okay, we don't have a lot of time, but trust me, we got through the hard stuff already. These are really, really fast limits. Let's do a few of them just to get the feel for it. And part A, let's let this be the limit as x tends towards 2. The function will be the natural logarithm of 9 minus x squared. Well, if we turn to theorem 7 above, it'd say logarithmic functions, regardless of the base, they're all continuous. 9 minus x squared is also continuous. So as long as 2 is in the domain of that function composition, we have full continuity on this whole entire thing. So let's take a look. It'd be equal to, by direct substitution, the natural log of 9 minus 2 squared. And that should be our answer. All we have to do is just simplify this down. As long as 2 is in the domain, then we've done the limit by continuity. It's just that fast. So this turns into natural log 9 minus 4 for the natural logarithm of 5. 5 is in the domain of the natural log function, so we're in business. That's the answer right there. Well, we did it, folks. That's the fastest limit we've ever done. Any questions about that so far? Oh, if we had, say, -5 right here in the limit?
Or just the end of
We would have to say does not exist in that case. Yeah, so the trouble with the logarithm function is its graph is going to look like this. Exactly. We can't even put 0 this time. It's exactly right. Strictly positive numbers. This is y equals natural log x. So whatever goes into 9 minus x squared, we have to ensure non-negativity right here for logarithm. Yeah, go ahead. Cosine tangent. I think I have an example similar to that. Let's try that next, if that's all right. Okay, so if we have a cosine and a tangent, here's part B. This will be the limit as x goes to, let's see, let me leave that blank here because I have a cosine, but I don't have a tangent. I want to make sure it comes out nice. Cosine of tangent of, I think pi would be a good one. Let's let this one go to pi. Sorry, say again? Pi, just pi radians. Yeah, so let x go to pi of cosine tangent x. So that ought to work. First thing we have to think about is this is a function composition, but that's okay as long as the component functions are continuous. Cosine's continuous, tangent's continuous. Oh, I think I see what you were meaning. If it was pi over 2, that'd be a point of discontinuity, and this would not exist. The tangent function is undefined at multiples of pi over 2, odd multiples of it. So we'd have to avoid all those vertical asymptotes. We're going to see some of those graphs coming up. But if it's just pi, tangent pi exists, and cosine at any number always exists, and it looks like this. we'll have cosine of tangent evaluated at pi. And if you're like me, if you haven't done trigonometry in a number of years, you might feel rusty. Occasionally, I'll put just supporting graphics down below. If you feel like you've got it right away, then just throw it in there. You're in great shape. But this is usually what I do. I'll draw a unit circle. I'll do this sometimes in class, especially when we do more and more trig in chapter 3. Pi radians is way over here. So I just need the coordinates. They're going to be -1, 0. And when it comes to trig, we can now say tangent at theta is sine theta divided by cosine theta. Everything orange is pretty much review, but I think it always kind of helps, especially after a long break. Now back to these coordinates. The first coordinate, is that going to be sine or is that going to be cosine? Good call. So we're in great shape. We can say tangent at pi is going to be first the sine value, second coordinate, divided by the cosine value, first coordinate. So the whole thing comes out as a 0, and we're ready to run with it. Does that make sense to folks on that evaluation there? Awesome. If trigonometry is pretty rusty, it's easy to happen for this class. One thing to keep in mind is our course text has an excellent review appendix on trigonometry. It's short, it's like 13 pages, has all the formulas you'd want, and it breaks it down from first principles like a extremely fast crash course. So really good to take a look at, even if you feel pretty fluent in trigonometry, it's good to just kind of shore up all those formulas and ideas. But going back to this is going to be cosine. We found that tangent at pi is 0, and cosine at 0, anyone recall what that should be? Exactly, good call. Let's put it here on the graph just to help. At 0 radians, we're right here. That's a 0 radian measurement. The coordinates go 1, 0. So cosine at 0 should be exactly a 1. So we did it, folks. This one could have been torture, right? But we picked a value that's in the domain of a continuous function. So all you have to do is evaluate it. There was no trickery whatsoever on this thing. Any other questions at all so far? Okay, let's do one more that does involve one small trick, and then we'll call it a night. Does that sound all right to everyone? Okay, one thing I haven't used is theorem H right here. I want to show how it gets used. It just wouldn't be fair otherwise. So here's our next example. So in part C, we're going to be taking the limit. This time it's for x heading towards 2 of arctan, for no apparent reason, just another way of saying tangent inverse, x squared minus 4 divided by 3x squared minus 6x. Now, part C is where things go a little bit awry for us. It's going to be more similar to section 2.3. Arctangent is continuous on the entire real number line. The inside is a rational function. It's only continuous on its domain. If we plug 2 inside there, here's what goes wrong. The denominator is 3 by 4, so 12, minus 6 by 2, so we get a 0 below. This doesn't work. Sorry, say again? Exactly. Oh, and above. So this one's just undefined. Oh, actually, 0 over 0 is also considered undefined, sadly. It doesn't even seem fair, right? But if a 0 is in the denominator, exactly, it's undefined. Yeah, error in your calculator, anything like that. So in this case, we can't even use direct substitution. But here's where continuity is helpful in a different way. So if we're continuous at b for the function f, that's going to be the arctan function. And if a certain limit exists, we're thinking about the function inside now. If that limit exists and equals say b, then you're allowed to take this limit operator and commute it inside the arctan function. That's a really slick way to use limits, and it works only through continuity. So if I suspect that limit exists and comes out as a finite number, we can and will still do this. So let's give this a try. I'd write immediately equals arctan limit as x approaches 2 of x squared minus 4 divided by 3x squared minus 6x. At this stage, I'm done with theorem 8. That was the whole punchline, that the limit on the outside can go right inside, just like we did right here. Does that make sense, folks, on the use of theorem 8? Okay, still no direct substitution, right? But our trick here is, let's just factor it and see what falls out. If we can factor this just right, we might still be able to take the limit. So on the next step, we can say that this is arctangent, or tangent inverse if you prefer. Limit as x goes to 2. The numerator factors as a difference of squares. Always a great formula there. It's x plus 2 times x minus 2 in the denominator, and that's a 6. Let me fix it. We can factor out a 3x, leaving x minus 2. That then gives this cancellation. And with what's left over, that's a rational function. 2 is in the domain of that. There's no division by 0 any longer. So now we're going to use continuity and say it's equal to arctangent. Putting 2 here will give me a 4 above. Putting 2 in the denominator will give me a 6 below. So this is arctangent of 2/3. That's not a friendly value, but it does exist. It's a nice number. And you have options when you go to do this in the homework. If you get a value like arctangent 2/3 or a value like natural log 5 even, you can calculate if you like, but I'd say the exact value is preferred. That's what you're going to see in the back of the book. And I would only calculate it to get a decimal number if you're curious. What is the magnitude of that number, or just for fun? So go for the exact answers there. And if you want to approximate it, that's always going to be optional. Well, any last questions, folks, on finishing off this section here? Okay, these are the main kind of things that you're going to see in the homework. When you go to actually do these limits like this, it's pretty fast. Just evaluate and simplify. But watch out for issues like on part C. You might occasionally have to do a little bit of work to simplify first, then take the limit. Well, have a great night, folks. And if you have questions, I'll be happy to help out.